Hi, in today's lecture, we will be discussing about probability. So by definition, we can say that an experiment is a process that, when performed, results in one and only one of many possible observations. The observations are the outcomes of the experiment. And the collection of all outcomes for an experiment is called your sample space. So let's have an example here. So for example, when you toss a coin, so that's an experiment, you toss a coin. One time, there are two possible outcomes, whether it's a head or a tail. And the collection of all your possible outcomes is basically your sample space, which is basically the heads and the tails. The same goes for rolling a dice. So you have a six-sided die, you roll it, you have six possible outcomes, getting a number 1, number 2, 3, 4, 5, or 6. And then when you have the sample space is basically the uh, the collection of all those possible outcomes that you have. So how about tossing a coin twice? So you have here now four possible outcomes. You get heads twice. You get heads first time and then a tail the second time. You get a tail first time and then a head a second time, and you get tail twice. So those are now four possible outcomes of tossing a coin twice. And of course, your sample space now becomes those four possible outcomes. So here is an example from the example a while ago. We can draw a tree diagram here. So for the first tossing a coin once, you have two possible outcomes, heads and a tails. If you do it twice, so toss a coin once, you get a head or a tail. If you got a head, you toss it again, second time. So it's either also a head or a tail. So as you can see, this tree diagram is more of an exponential type of a diagram. So you now have four possible outcomes. So another example. So suppose we randomly select two workers from a company and observe whether the worker selected each time is a man or a woman. So what are the write all of the outcomes of this experiment and draw a tree diagram. So selecting twice or select two workers. So the first time you select a worker, it can be a man or a woman. The second time, it's either of course a man or a woman, but since this is second selection, so times two. So you get four possible outcomes. So an event is a collection of one or more outcomes of your experiment. So we can have either a simple event, which includes one and only one of the final outcomes of an experiment. So this is a simple event, it's only one outcome. So here, again, the example from before, when you select two workers from a company and observe whether the worker selected each time is a man or a woman. So you have four possible outcomes, and the simple events for them is, of course, each outcome. So outcome 1 is two men. That's event 1. A possible event is the second outcome. A man first and then a woman second. And then another one, event number 3, is a woman first, then a man second. And the fourth event, which is also the fourth outcome, is two women. So when you have a compound event, on the other hand, it's a collection of more than one outcome for the experiment. So again, from the previous example of selecting two workers from a company, so let's say A be the event that at most one man is selected. So at most, that means that a maximum of one, the man, or it's an event where it's a male, a maximum of one time, or at least the selection is at most or has a maximum of one male in the selection. So what are those outcomes? So we have here the four outcomes. Two males, of course, it's no longer included in the requirement. At least, at most one man. This was included because it's one man, one woman, and then one woman, one man. So again, also included in the event A. And here, two women. Since the idea is at most one man, so it's just a maximum of one. So 0 is considered also. So these three events, or rather these three outcomes, is the event A, where at most one man is selected. So this is an outcome, or rather an event that is consists of three outcomes, three possible outcomes. So this is called the compound event. Now, if the event here is just a one outcome, That's a simple event. So in the case of here is two men is selected. That's just a one outcome of all one out of the four possibilities. So this is a simple event wherein you have two men are selected. So are we clear? Okay, now we have probability. Probability is the numerical measure of the likelihood that a specific event will occur. So take note, it's a numerical measure. We are assigning value here, a numerical value, which is how likely a certain event will occur. Basically, a measure of how likely a certain event will occur. So the probability of an event always lies in the range of 0 to 1. So we have here two properties. The first property is, of course, this one, the probability that an event will always lie in the range of 0 to 1. So the probability is between 0 and 1. So that's a simple event, or whether it's a simple event or a compound event, it's always within the range of 0 to 1. So the sum of the probabilities, the second property is that the sum of the probabilities of all simple events or the final outcomes of an experiment is always 1. Basically, the sum, this is the second property, and we actually denote it as such, that the sum of all events or all outcomes of your experiment must always be equal to 1. We have three conceptual approaches to probability. So the first one is classical probability. In classical probability, two or more outcomes that have the same probability of occurrence is said to have equally likely outcomes. Basically, you have here an experiment where each outcome of the experiment has an equal number of, or rather have the same probability. That means they are equally likely to occur. So just like heads, tossing a coin, heads or tails, you get 50-50 of each. So here is a simple way to actually look at classical probability is just to calculate the probability of the certain event. If it's a classical probability, if it's a simple event, that's one outcome over the total number of outcomes for the experiment. Or if it's a compound event, just count how many outcomes is included in that event, in that compound event, over the total outcomes, all of the total possible outcomes of the experiment. So let's have an example. What is the probability of obtaining a head and the probability of obtaining a tail for one toss of a coin? So this is just a simple how many outcomes first that we have. So in a toss of a coin, you have either head or a tail. And since they are equally likely to occur, you just have we'll just apply classical probability. So the probability of getting a head, that's just one event or one outcome out of two possible outcomes. So this is one, since a simple just one event, and you have two outcomes. So 1 over 2, that's 0.5. That's the same way with getting a tail. So one outcome is the tail, and there are two possible outcomes. So 1 over 2, that's 0.5. So another one, what is the probability of getting an even number in a roll of a die? So this is a compound event. So in a six-sided die, you have the even numbers 2, 4, and 6. So you have basically three events or three outcomes here in this compound event. So the probability of getting an even number is the number of outcomes, or rather the number of outcomes in your event, which is the compound event. So you have three possible outcomes, and how many total number of outcomes you will get. So in tossing a six-sided die, you have a total of 6 possible outcomes. So that's your denominator. So 3 over 6, that's also 0.5. So another concepts or approach to probability is the relative frequency concept. So using relative frequency to approximate a probability. So this happens when you do an experiment, you repeat an experiment several number of times, so n number of times, and a certain event A is observed f times. So that's a frequency that the event happens when you repeat the experiment. So that's your relative frequency. This is basically how often that you get that particular outcome when you repeat the experiment. So the calculation of the probability using the frequency approach is, of course, number of frequency from past experiments. This happens when you have, well, basically past experiments. From past experiments, how frequent was that certain event occurring over the total number of times you repeat your experiment. So let's say, for example, 10 of 500 randomly selected cars manufactured at a certain auto factory are found to be lemons. When we say lemons for a car, that means it's a defective. It has a factory defect. So that means that in a factory, you have 500 randomly selected cars and 10 of them turned out to be defective. So assuming that the lemons are manufactured randomly, what is the probability that the next car manufactured at this auto factory is basically defective? So the solution here is, if you have from your sample size is 500 because you randomly selected 500 cars. And the times that you found a lemon in there or a defective product is 10 times. So the probability of having a defective car in the next time a car is manufactured is basically F over N. So 10 over 500, that's 0.02. That's the probability of that. And getting a good car, of course, is just since this is application of the second property where the total number is equal to 1. So if the probability of getting a bad car is 0.02, therefore the probability of getting a good car is 1 minus 0.2, which is 0.98. Or we can just approach this as a frequency. So that means 10 times you found a bad car, and the rest of the time, that is 490, you found a good car. So 490 over the total number of times you tested, this is 500. So 490 over 500, 0.98. So the probability of getting a good car is 0.98 or 98%. So we also have the law of large numbers. So if here, this is a corollary to the frequency approach. If you repeat the experiment multiple times, the probability of an event obtained from the relative frequency approach is the actual probability, because the frequency probability is just an approximate of what is the actual probability. So if you repeat the experiment hundreds, thousands of times, you will approach the actual outcome of the score. So basically here, the sample size matters. The number of times you repeat the experiment matters a lot. So for example, here is a toss of a coin. If you do the toss of a coin, we all know that in a toss coin, it's a 50-50 chance. But when we actually perform the toss coin, for example, you toss the coin 3 times, and every time you get a tail. So the probability that you get will be 100% probability of getting a tail and 0 probability of getting a head, which is actually adverse to what our understanding is in classical probability, which is that both of them has a 50-50 chance. So we increase the number of tosses that we have to 8. And the number of heads, so another experiment is the number of heads is 6, the number of tails is 2. So now the probability of getting a head is 75%, the probability of getting a tail is 25%. So again, it's a long way off to 50-50 or 50% of each. So that is for 8 times. Then we increase it until we reach, say, 1,000,000 coin tosses. And the number of times you get a head is 500,313. The number of tails you get 499,687. So you get a probability using the frequency approach, 0.5003 for getting a head and 0.4997 for getting a tail. So when you repeat it multiples, actually this is 1,000,000 times, you will get a very, very close to what we know of what classical probability is, that you get a 50-50 chance of getting a head and a tail. So here is what you mean by the law of large numbers. If you have a very large amount of sample size, the number of repetitions, it will approach what is the true value of that probability. So if the experiment is repeated only a few times, the probabilities obtained may not be close to the actual probabilities. As you see here, 3 times or 8 times is actually quite far. But if you increase the number of repetitions, the probabilities becomes very close to the actual probabilities. Now, why do we need to just simulate this coin toss when we already know that the probability of getting a heads or tails is actually 50-50, because classical approach says so? That is because classical approach is only applicable for equally likely scenarios, where of course, heads and a tails, we all know, it's a known fact that it's a 50-50 chance of getting a heads or tails. What about, for example, say, when you go out, what is the probability of that you will encounter a person infected with COVID? So how you do not really know whether it's a 100% probability or not. So you repeat it 100 of times and then you tally the score of getting COVID whenever you go out. Basically, you might, well, it's a morbid example, but that is where we actually do the frequency distribution approach when we really do not know if the probability of getting infected or not whenever we go out is unknown. Is it 50-50 or is it not? We do not know if it's 50-50, whether you will get COVID when you go out is equally likely as not getting COVID when you go out of your house. So basically, the measure when the scenario is like that, the way to calculate probabilities is the first one is of course frequencies. You repeat the experiment multiple. I'm not saying that you go outside multiple times just to get the probability of yourself getting COVID, but that's just a really morbid example. Sorry. So basically, the simulations, this occurs whenever we do not really know, whenever the outcomes are not equally likely to occur, and we don't know how likely is each other. That's why we need to calculate them. So let's have an example. Allison wants to determine the probability that a randomly selected family from New York State owns a home. How can she determine this probability? How is the housing in New York? So there are many factors here, but the simplest one is since whether you own a home or you do not own a home, these are not equally likely, the classical probability rule, you cannot apply classical probability of 50-50. You just get one outcome and then total over the total number of possible outcomes. It's not. Here you need to approach it as a relative frequency approach. You test people from New York State multiple times and then count the number of times you get a response where it owns a home, or count the number of times it doesn't own a home. And then the frequency over the total number of times you approach or you ask that question, that is your probability. So the third one, the third conceptual approach is subjective probability. This is the probability assigned to an event based on subjective judgment, experience, information, or belief. So this one is a bit ambiguous because there are no definite rules here. You just feel that, for example, when you go out, uh, for example, here in Venezuela, when I go out, out of my home, I feel that I will get a 25% chance of passive of getting COVID, for instance. So because there are no COVID cases here in our neighborhood, for example, so it's highly unlikely for me to get COVID, so I'll go out. So that's a subjective one because I really don't know if it's true or not. It's just my feeling, and I'm basing that because there are no no COVID cases that I know of in my vicinity. So that's a subjective probability. So just a belief, a subjective judgment, or say experience.